Okay, this is Jack Jackson. I want to draw your attention to this document called Summary of Transformations of Relations in Symmetry. And this document basically is a 12-page document that basically goes along and gives an overview of all the different kinds of transformations that we're going to be looking at this semester, or that we have looked at. Hopefully you've already looked at these things, and this is a summary. Now, there's been a series of videos on these earlier from these notes, and then you actually have these notes here that you could print out if you need to for your work. Talks about transformations in general at the beginning, then talks about translations with some examples, vertical and horizontal, then general translations. Talks about things like what do you need to define a translation, what are the fixed points, and so forth. Then we talk about vertical and horizontal strains, like compressions and expansions. Then dilations, which are basically strain with the same thing in both directions, so it's a size transformation. Reflections. Reflections are harder in general, but we look at some specific ones about the y-axis, the x-axis, and the over the line y equals x. There's another video about this one here because this one's very important about inverse functions, so we'll talk more about that later, or hopefully, well, it may be later than this or earlier than this. Either way, it depends on the order you look at it. Probably you're watching this first and then some more detail on that later. And one specific rotation that we get is a 180-degree rotation about the origin, and this relates to something called even and odd functions. And then finally we have this one-page summary here for transformations. And notice we've talked about horizontal and vertical translations, translation by vector HK, reflection over the x-axis, reflection over the y-axis, reflection over the line y equals x, and a 180-degree rotation about the origin. All of these are the ones that give you congruent images. In general, your types of transformations that give you congruent images are, well, the identity transformation that doesn't do anything, and then the translations, rotations, reflections. There's another thing called a glide reflection, but a glide reflection, all it is just a translation and then a reflection after that. And so really they're just built up out of these kinds of transformations. These are called isometries or rigid transformations, which map a pre-image to a congruent image. And they preserve distance and angles. A dilation is a similarity transformation. It gives you a non-congruent image, but it is similar to the original image, so it preserves the angles, but the distances are proportional. Strains are stretches and compressions, expansions and compressions, and they can be done in the horizontal or vertical way pretty easily. And those give you images that are neither similar nor congruent. They give us images that are don't preserve either distances or angles. Here it talks about the fixed points. There are no fixed points on any kind of translation, so none at all. Reflections, the points on the mirror line are fixed. So a reflection over the x-axis would fix those on the x-axis, and so forth. When you have a rotation, actually a rotation or a dilation, the only fixed points are the center of the rotation or the center of the dilation, and in our case the only ones we're looking at are the ones in the origin. We are doing translations in general. We can see how to do a general translation, but the rest of these we're only doing specific examples. We're not doing all possible reflections, only these three particular ones here. We're not doing all possible rotations, only this one type of rotation. And again, we're not doing all dilations, but only ones that are centered at the origin. We're not doing all strains, but only vertical and horizontal strains centered up on the x or y axis. When you have a strain, you have a line that's your axis, and that points on that are fixed. So basically just remember that the formula is, we can describe the change in the formula, the change in the table, and the change in the graph. The change in the formula is always going to be in the form replace blank by blank. And the formula is basically backwards from everything else. So if we replace x by the opposite of x and leave y alone, of course we do leave y alone in the table, but what we're going to do is actually add h to the x values. So if you replace x by x plus 2, we're actually going to subtract 2 from the x's. If you replace x by x minus 7, we'll add 7 to the x's. Leave y's alone. Similarly, if you replace y by y minus k, we'll actually add k to the y values. You can, of course, do both of those things and get a general translation. Okay? And so, translations, what do? You move them about. So you change the sign on x, not change the sign, change x to x plus or minus a number. It's going to slide it sideways, a horizontal translation. Whereas if you replace y by y plus or minus a number, it's going to move it up or down, sliding it. Of course, if you do both, it's going to slide it maybe at an angle to a new place, sliding by the vector hk translation. If you change the sign on y, you end up changing the sign on y in both the formula and the table, and that turns out to be a reflection over the x-axis. If you change the sign on x, that's going to reflect over the y-axis. If you switch x and y, that gives us the inverse relation, which is the opposite steps in the opposite order, and that's also a reflection over the line y equals x. If you switch the sign of both x and y, which will happen both in the table and the formula, then it's two flips, one about the x-axis and y-axis, in either order you want, and it turns out that that gives you a graph that is rotated 180 degrees about the origin. If you replace x by x over a constant, then you are straining it or stretching it in the horizontal direction. So what you're really doing, if you replace x by, say, x divided by 3, then what you really do is multiply all the x values by 3, leaving the y's alone. And so that's going to stretch it 3 times as far away from the y-axis. And similarly for when you change y, we get that. We get replace y by y divided by constant gives you a vertical stretch or compression. In the examples that I give over here, you can see that the pre-image is always this y equals the square root of x, which you can always see in red in the graph. The image is various colors, but the image is there, and you see the formula for it, and you can you see I picked one point on the graph so you can see numerically what's happening. So for example, in this first one we replace x by x plus 5. Notice we left the y alone. 1 1's on the original. We left the y alone as 1, but to the x we actually added 5, which means we actually subtracted 5, excuse me. So the x is now -4, and the graph shifted to the left. The next one I did y plus 8 equals the square root of x, so I replaced y by y plus 8, and so what you really do is subtract 8 from all the y's, so 1 1 becomes 1 -7, and that's shifted straight down 8 units. We did sort of combine those in the next one. We replace y by y plus 6 and x with x plus 10. So what we really do is subtract 10 from x and subtract 6 from y. So 1 1 gets mapped to -5, -9. And so every point on this pre-image gets shifted, and it's shifted actually 10 to the left and 6 down. So it's shifted by the vector -10, -6. The next example you see here, we got y equals square root of x. 1 1 gets sent to 1 -1 because we're replacing y by -y to get -y equals square root of x, and that's going to flip that graph over the x-axis. We can flip over the y-axis by changing the x to -x, so it's y equals square root of x, and so now it flips over to the second quadrant, whereas the one before flipped over to the fourth quadrant. So 1 1 goes to -1 1. The next one, we started with y equals square root of x. We switch x and y to get x equals the square root of y. That is the inverse relation of this one. And so 2 4 gets sent to 4 2. We're just simply swapping all the order pairs, swapping the coordinates. Next, we change the sign of both x and y. That's going to rotate the first quadrant graph all the way around to the third quadrant, and so there's our green image down there. And so 1, 1 goes to negative 1, negative 1. A congruent image in the third quadrant, a rotated image, a 180-degree rotation about the origin. The next one is a dilation. So I replace y by 2y and x by 2x. So what I'm really doing is dividing the x's by 2 and dividing the y's by 2. So 1, 1 goes to 1 half, 1 half. And so this is a dilation. Everything's moved actually toward the origin, directly in a straight line from the pre-image toward the origin, halfway. And that'll be the image point. The next one, we have y equals the square root of 3x, so we've replaced x by 3x. So what we really do is multiply the x's by 1/3, or divide by 3. And so 1, 1 goes to 1/3 1. And so this is going to be a horizontal compression, so it's going to be 1/3 as wide. Same height, but 1/3 as wide. The next one, 5y equals the square root of x. This one is going to be a change in y, so its y is replaced by 5y. Means what we really do is multiply the y's by 1/5, or in other words, divide by 5. And so 1, 1 goes to the point positive 1/5. And so all of the y's are 1/5 as tall. 1/5 is as much as they used to be, so it's shorter. Same width, but shorter. Now let me finally finish up with just a couple more examples. And this last example down here on this GeoGebra thing, I can let's set everything back to the sort of the status quo here, where the identity transformation. So we set a back to 1. Whoops, too far. A is 1. Now we're going to set b to be 1 as well, and h to be 0. And we start with some function like this one. If the way this particular formula is set up here for the red transformation, I've taken the formula and I've done things in the following order. Okay, I started with y equals some function of x. In this case, y equals y. Let's try this again. I started with some function of x and have y equals that. So in other words, y equals square root of x is our example. The first thing we do is do any kind of stretch and or flip. And you can actually do these in either order. You can either replace x by x over a first, change a first, and then change b. Those can be done in either order. In fact, the x changes and the y changes are kind of independent of each other. But let's say we do both of these first, and this will give us our stretches, and if it's one of these is negative, our flips. So for example, let's say the first thing we do is we change the a, and I'm going to make it, let's say 3 times as wide. So stretch it that way. Let's say we change b to a negative 2. So we flipped it and stretched it vertically. Okay, so let's back up and follow one of our points here. Okay, so here's B13, which is 1, 1. Where does it go? It goes 3 times as wide, so it stays the same height, but now it's at 3, 1. The next thing we're going to do is divide by negative, b is negative 2, and it's division over here. So we're going to divide by negative 2 in the formula, in the actual table. What we're going to do is multiply by negative 2. So now this what was y was 1 up here, now it's now at negative 2. So this is still the image of that one here. Next, and this is kind of important that we did it in this order. Next we're going to do our translation. So next we do the translation by replacing y by y minus k and x by x minus h. Okay, and so that is going to give us our new thing. So this is going to stretch, this is going to shift. So let's say I shift 4 to the right and then maybe up 1. Okay, and so our final image of the point 1, 1 was down here. But notice how we thought of this in the order. And in order, it turns out, does make a difference. Okay, now if I solve this for y, I'm going to multiply by b first. Okay, so over here that's y minus k is b times the square root of this. And then I'm going to add k. So there's our general formula if we have any function. Our specific example is y equals b times the square root of x minus h over a, and then you got plus k on the outside. And if you look, that's exactly the formula that we have. Well, we have both of these. We have the general and the specific in here. The general is right here, y equals, and then b times f of parentheses x minus h, two parentheses there, then x minus h, close parentheses, divided by a, close parentheses, plus k. So in our case, that's negative 2 times x minus 4 over 3 to the 1/2, or square root, plus 1, and all that's equal to y. That's our final red relation. But notice it does make a difference if we do this in a different order. So let's look at an example of that. Let's say we start with y equals, just y equals x squared, good old friend there. Okay, so the purple graph is y equals x squared. Now let's just change the x, but let's do the order different. Let's say shift 3 right, and then twice as wide. Meaning, what I mean by that really is twice as far from the x-axis, the y-axis. So shift 3 right is replace x by x minus 3. Twice as wide is replace x by x over 2. So if we did this in order, shift 3 right will take you to x minus 3 and then square, and then twice as wide would be x over 2 minus 3 square. So let's check that out, and let's actually do the intermediate steps. So the first step would be replace x by x minus 3, and that's the original graph shifted over. The next one, when I replace x by x divided by 2, it's twice as wide of the red graph, not the purple one. Now what happens if we do that in the opposite order? Okay, sometimes it doesn't matter, but most of the time it does. So if we start with y equals x squared, and then the first step we make it twice as wide, so replace x by x over 2, we get y equals x over 2 quantity squared. And let's take a look at that. So there's our first step. We made the purple one twice as wide, and then we're going to shift that one by 3. Okay, so let's try that and see if that turns out to be the same or not. So take that one and replace x by x minus 3. And sure enough, it is not the same as the red one. I know I've got a lot of graphs here, but if we get rid of the intermediate graphs, that one, oh, something funky happened here. There we go. And this one. Now we only have the original purple graph and the two possible images, and you see that the red and blue images are not the same. So the order you do these things does make a difference. The order of shifting and stretching for X makes a difference. The order of shifting and stretching for Y makes a difference. The X and Y doesn't make much difference whether you do a shift left or right or a shift up or down first. That doesn't really make any difference. But it does make a difference within X and within Y. So you kind of have to be careful which order you do these because it does make a difference. And this particular sketch over here, where is it here, actually assumes that it is a, if you look at the way this is done, we did this, that's the one where we did the stretch first and then the shift second in both cases. We could do it the other way around if we wanted to, but that's just not the way I set this particular one up. Okay. Some cases you can think of it more than one way. If the thing continues on forever. So if you have something like y equals x squared, which has domain all reals, goes on forever, axes here, okay, you can think of y equals, let's say, 4x squared. You can think of that as a change in y or the change in x. As it's written, it's not really either one per se, but you could write it as y over 4 is x squared, which I think is the most natural way. And now we see that y has been replaced by y over 4, and so this is going to be a vertical stretch. Vertical expansion, a shear. I mean, not shear, a strain. And so this is 4 times as tall. Well, this 4 times as tall going to make it, could we think of it as skinnier instead? It's narrower. Well, we can if we think of it as y equals 2x squared. But notice it's not a 4 in there. It's not 4 times, it's 2 times now because we had to bring it inside the square. And so that's actually, we can now think of it that way as replacing the x by 2x, and that is going to be a horizontal strain, this time a horizontal compression. We really divide the x's by 2, so it's half as wide. So if you were just to graph this one here, you can think of it as 4 times as tall, or you can think of it as half as wide, but it's not 4 times as, it's not 1/4 as wide or twice as tall. You know, you can't do it both ways. There is a relationship, and it's a little bit more complicated. I think this one right here is the most natural way to think of it, but it can be done the other way as well. That's if it's going on forever. Now, if you had a very specific, let's see here. Let's say we got the origin, we got negative 1, 1, positive 1, 1, and 2, 1, 2, 3, 4. Let's just say we have that much. And this is part of y equals x squared, but it's only the part for x is going from negative 1 to 2. So this is negative 1, this is 2, and here are your axes. Whoops, should be on that line there. They're the axes, right? And where are the y's? So the domain is negative 1 to 2. The range is from 0 to 0 to 4. Okay, and so that is going to be what we have here. And so now if I do some transformations on this one, since this has a finite, well, no, it's not finite, it's infinite, but it's bounded, a bounded domain and range, then we have to be a little bit more careful. So if I were to take, and the formula is y equals x squared, but it's with this restriction. So if I were to go and say I want to say shift right 2, then I'm going to replace x by x minus 2 in the formula. It's not going to change the y, so they're still going to go from 0 to 4. But the x's, I'm going to actually add right 2. I'm going to add 2 to everything, so it's going to go from 1 to 4. And so now everything goes to right 2. This one goes to here, this one goes to here, this one goes here, and this one goes here. And so we have it go like that. So if we do a stretch now, let's say we do the same one, and do a stretch, so we go from here, so we did it in stages, from there to there. And now we go for another one. Let's say we're going to go expand horizontally, centered on the y-axis by a factor of 2. Okay, so in other words, twice as wide, twice as far from the x-axis. We can just do it. This one's 1 away, so now it's 2. This is 2, so now it's 4. This one was 3, so now we're out to 6. So notice it's wider. And this was at 4, now it's at 8. Kind of getting on top of my other drawing, not so good there. But this is the graph that we end up with here. Well, what happens to the domain and range when we do that? Well, again, we're leaving y's alone, so notice they didn't change. They still went from 0 to 4, but the x's are going to be, everything's going to be twice as big, so it's going to go to 8. What's the formula? Well, I replace x by x over 2. So there's your formula, but it only applies in that region. So notice I have to get my regions right, I have to basically do my transformations to my interval as well. Now if I make some vertical transformations, I can do those as well. Alright, I think that's going to be a good place to stop there.